First, I would like to thank the organizers, especially Professor Yonglan Li for inviting us and organizing this workshop.
Your name in Chinese.
Okay. Spring water. Yeah. And the title is Poisson homology and cohomology over smooth varieties. But I will do it in algebra way. First, let me start from some background or motivation. If X is an orientable real manifold, real Poisson manifold, then we can define Poisson cohomology. That's defined by multi-vector fields. And this is isomorphic to the differentials if this is of dimension n. And we have isomorphism here. And we have a Poisson chain complex. Okay. Yeah, in fact, if it is orientable, we can get the isomorphism here. And if phi at is a so-called modular vector fields, I will define it in algebra way. Then this is commutative up to, if we start from a multi-vector field here, P, and we go this way, this up to this one, because phi eta will be a vector field. If we take wedge product with P, we get a P minus 1 vector field. And one term is this one. And if the modular vector fields is 0, in fact, that means X is so-called unimodular. Then we get, because this is 0, so this is commutative. So we get the Poisson cohomology. X is always isomorphic to the Poisson homology X, homology of X. That means the Poisson duality. And in the last workshop, I put something in algebra way. If R is a polynomial Poisson algebra, general polynomial Poisson algebra, and I defined the modular derivation, and in some sense, this is always commutative. Then I proved the so-called twisted Poisson duality. Today I will do, in general, today I will assume R is a smooth variety, Poisson variety. Okay, smooth maybe smooth Poisson algebra way. And let me start from multi-derivations. And differential forms. In fact, we know the color differential form, so this is relatively okay. It's an R module with a derivation from R to these so-called color differentials. And if there is a derivation here to any R module, then this color differential solves the following universal problem. We can find R morphism here, unique R morphism here, so that this is commutative. That means for any R module, if we take the morphism, R morphism here, then we get a one-to-one correspondence from the derivations R to M. That is FD go this way, and this just says this is the inverse. Say, if R is a polynomial algebra, then we know the color differentials is just the free modulus over R of rank n. And if R is this algebra, the sphere, then the color differentials is something looks like this. The rank 3 R modular the submodule generated by x dx, y dy, z dz. And this is so-called stably free, but not free. Stably free means if we put another copy R here, this equals to 3 copies of R, but not free. And the color differentials, not like this. This is the nth dimension, and it's generated by n elements. Is the number of generators is equal to the dimension, but in this case, it's generated by at least 3 elements. At least by 3 elements. And but the global dimension or the smooth dimension is equal to 2 in this case. And so the following, I assume R is smooth, and this implies this is always finite generated projective module. But if this is domain, this is equivalent. So in this case, and I suppose, because this is the finite generated projective module, then there's a dual basis for this module. So I suppose dx1 dxr, okay, maybe I like this way, dxi and dxi star. dxi star is the dual module of this projective module. It's a dual basis for the color differentials. Okay. And as we see in the last example, R is usually greater or equal to the global dimension of R. And it may happen R is greater than this one. And then we'll see for any A in R, the differential by using the dual basis is equal to this one. This acting on dA and the dxi. This is the dual basis set. And as we see, we can view this one at the derivation. If we take this is R, then this, in fact, this dx star, we can identify it with, by this isomorphism, with the derivation here. So we can view dxi star at the derivation and acting like this. So this is like the partial derivatives in polynomial case. And by the dual basis lemma, we see the derivations from R to R is the dual modular of this one. And this is the double dual of this one. So we can find the dual basis over this module. And the dual, we write this way. Then there's a dual basis here. It's dxi star is a derivation. And by taking the evaluation map of dxi is here. Okay, this is there, yeah. And this is evaluation map here. Then for any derivations from R to R, then this one is equal to, this is also by the dual basis acting on this one and the dxi star. And because this is evaluation, so this is just psi. Okay. This A. Yes. Yeah, okay. Maybe I don't need this one. This is by the dual basis, and this is by the evaluation map. This is xi dxi star. So again, this is like the partial derivatives. So in general case, we replace dxi star. Yeah, we replace this one by dxi star. So in general, omega p r is the wedge product. P is wedge product of the Kähler differentials. And the elements here we call the p forms, p differential forms. And we define chi pr. Chi pr is all the skew symmetric p linear forms from R to R to maybe in general, if M is a module, to the general way, M is R module, and such that F is a derivation in each argument. Then just like the p equal to 1 case, we have an isomorphism here. The morphisms between R and M is isomorphic to chi Pm. And because R, we assume R is smooth, then we can prove this one. The wedge product of projective module is also finite projective. It's also finite projective. And then we can get the dual. We take the dual again. We get we take the dual again. That's the double dual of omega PR. The double dual is isomorphic to this one. And we can find a dual basis with dual basis. This, we can find the dual basis here is something like this one, dxi1, dxip, and dxi1 star. dxip star. And use this, we can get, in general, if we take the wedge product of the derivation of R, because this is R module, then there's a natural map to here, chi PR. Something like this, if we take psi 1, is a derivation, and say we can define a map here of psi 1, psi p, and it's a p derivation like this, a1, ap. To keep the skew symmetric things, we use the determinant, and it maps to something like this, sigma, the permutation of p elements with a sign that is psi 1 a sigma 1 and psi p a sigma p. We use the determinant to define this one. This is well defined, always well defined. And as we see, this is isomorphic to this one. That's by definition. And if omega 1 is projective, then by using this dual basis theorem, we get this is equal to, this is just the dual basis theorem tell us. This is always isomorphic. And we know this copy is isomorphic to this copy. So we get this isomorphism. So in general, if R is smooth, we get this one. This is also always isomorphism. That means the multi-derivations is just a wedge product of derivations, just like in the local case of manifold factorial case. Okay.
Field is real or field is always real field?
No, is any, but I need the characteristic is still no. Characteristic. And so, in fact, we know something like the Poisson co-chain complex like this. Just replace this one by R, this Poisson chain complex here. So then the next thing I will define the deck P, how to define deck P. So I need a so-called contraction map. And for any P derivations, then I can define an IP from the Q forms to Q minus P forms. Okay, if Q is less than P, then we just set this to 0, and we suppose Q is greater than or equal P. And for any Q forms here, and we can get a Q minus P forms like this, A0 here, and P acting on the first P elements. But I need to keep the skew symmetric property. I use this one. Sigma is a so-called shuffle, perpetual shuffle. So P, Q minus P shuffles. That means sigma Q such that sigma 1 less than sigma P, and sigma P plus 1 less than sigma Q. That's a P, Q minus P shuffles. A sigma 1, A sigma P, and D acting A sigma P plus 1, D acting on A sigma Q. So this is a Q minus P forms. This is in R. So that's one contraction map. And for any Q forms, PQ. And we can also define a contraction map from Q, that's P maybe, Q forms to Q minus P forms in the following way. That means if this is F and IQF should be Q minus P forms, and they can acting on, say, dA1, dAQ, dAQ minus P. So maps to, okay, F dA1, dAQ minus P, and wedge Q. This one. And in geometry case, we need this condition orientable. That means the canonical bond is trivial. So I need another assumption. Okay. In the following way, I assume further the canonical bond omega nr is trivial, is free of rank 1. And eta is called the volume form. Then I can define deck PM for any R module, a Poisson module. Here, this is for any module is okay. Yeah. So type PM to M tensor omega M minus PR for any R. Like this. Is P. I take to this one. IP at IP is just like this one, but I write in general form. This case is just equal M equal to R. So in this case, it's M tensor. Okay. IP eta. Okay. I should define this one, and eta is in general is an M form. M form if for M form, general M form, DAN IP eta defined as is IP acting on this is equal to a 0 sigma PQ minus P, and P can acting on dA1, dA sigma 1, dA sigma P. And in this case, because P is at P derivation from R to M, so this part is in M. So take this one, dA sigma P plus 1, dAQ sigma Q. And this is the Q minus P forms here. And maybe yes. And we have this. This one, as we said, this is the dual of the P forms. This is always isomorphism. And if R smooth, this is a finite generated projective. This one is a finite generated projective. So this homomorphism is just, there's a canonical isomorphism from here to the dual module of this projective module. And this one is just equal to the P derivations from R to R, this part. And if okay, and we can find this one, M minus P R. This is isomorphism. We have a map here, that P R, M minus P R. We have map here. And in fact, we can find inverse map from this one to this one by if this is Q, we use I add a star Q here. I add a star is the dual of the volume 4. And it's n derivations. Then we can get the map here. So this is isomorphism. This is always isomorphism. And in fact, if we take the map here, take PM here, and this is always, we can check, this is always commutative. So we get, for any module, this is isomorphism, take PM. Okay, now let me define. So for the modular derivations, this is something like the modular vector fields in manifold case. We assume R smooth with tube of dimension n with trivial canonical bond R eta. Eta is a volume form. Then we define a map phi eta from R to R. And okay. Okay, if A is in R, and R is a Poisson algebra, I need a Poisson algebra. That means R is a K algebra, but with a Lie product. And the Lie product is a derivation with respect to the neutral product of the algebra. Let's suppose. For the real manifold case, that just means the smooth functions is Poisson algebra. And then we usually define this one is a Lie product of A with something else. This is, as I said, this is a derivation with a neutral product. This is a derivation. And we call this is a Hamiltonian vector field or Hamiltonian derivations. And because this is chi1 r, right? This is chi1, so we have defined IHA, the contraction map, IHA. So IHA is degree m minus, okay, if it's a -1 map, degree is -1 map. If we're acting on eta, this m form, then this is m-1 form. M-1 form, you use the lambda derivation here, we again get the m form. M form, that means it always belongs to this one. But because this is a rank 1 free module, so we can get A is multiplied to phi eta is defined by this, because DIHA eta is in this one. So this is something like a scalar multiply this one. Because we know this is a scalar, so we define this phi eta A. Phi eta is called modular derivation. And we can prove this is indeed not only a derivation, but also a so-called Poisson derivation. That means it keeps the Poisson product. That means if phi acting the Poisson product, then it's equal to phi eta A, the product of this one, plus A phi eta B. So this can be represented an element in the fourth cohomology. Fourth cohomology, Poisson cohomology. So, say if R is the polynomial Poisson algebra with a Poisson product like this, and we take the volume form like this, dx1 dxn. This is a volume form, and we can find say IHA eta dx1 dxn. This is defined by the shuffle product, but P is equal to 1. So if sigma 1 HA, sigma 1 is I, so it's something like this, sigma 1. Then the other is sigma 2, then is because the shuffle is like this, we delete this one, dxn. And for all the sigma is just I equal to n. Then the sign sigma is just, in this case, I minus 1 case. So if we D acting on this, then it's D acting on this one, then we can get I equal to 1. And the differential of this one, this is just the D product of A with xi, and this is j equal 1 to n partial A xi partial xj dxj dx1 dxi dxn. But if j is not equal to I, this is 0. If j equal to I, we can move xj to here. So we get this is just equal to j equal to 1n partial A xj partial xj eta, something like this. So we can get the phi eta A is just this part, A xj partial xj, something like this. And in the general case, that's very complicated because, as I said, R, the general letters of the omega 1, is greater than n. So the shuffle is very complicated. So in general case, then we can find phi eta A is something like this. Sigma I equal from, okay, S equal to 1 to R EXS star. As I said, this is just like take partial derivatives. And this is AXS. This part is something, is just like this. Just like this, because this is just like to take partial derivatives. And we have another part. Another part, okay, I like this, I belong to S, AI, A and BI. Let me explain this one. What is S? The big S, where big S is all the set like this. Okay, I1, I2, IN. I1 greater than 1, IN less than R. If n equal to R, there's only one possibility, the 1 to n. But in general case, there's more. And what is AI? AI is the dual basis. If I looks like this, acting on the volume form, that's AI. And what is BI? BI is at the star, the dual of the volume form. That is m vector, that n derivations acting on dxi1, dxin, something like this. And this is a general form of the modular derivations. And if r equal to n, then there's one possibility here. Then we can get AI is equal to BI inverse. So this is just, in this case, it's just AI inverse, just one term, and AI A. And in polynomial case, this should be in K, because invertible. This if this in K, this is always 0 in polynomial case. But in real manifold case, we can take log inside. Get this one is a Hamiltonian derivation. We can get a Hamiltonian vector field. But in general, there's one term here. And in fact, if we change the volume form, let's if we change a volume form here, then we can get phi is phi eta. Okay. So U, something like this. Okay. So we should modify the definition of unimodular Poisson structure. Okay. R is called unimodular if phi eta is something like this. Something like this is we call this is log Hamiltonian. It's log Hamiltonian derivation. And in polynomial, even in polynomial case, log Hamiltonian is usually not Hamiltonian. Okay. Hamiltonian is usually okay. Yes. Yeah, log Hamiltonian is usually not Hamiltonian. I will give an example later. So now I can say the duality. That means if R is a smooth Poisson algebra with trivial canonical bundle and also of dimension n, M is a Poisson module for any general Poisson module. Then we defined this chi p m plus n. This is something like, in fact, the Lie homology case. We can define the Poisson coefficient complex, delta p coefficient complex. And I said that this is isomorphism, m minus p m. There's isomorphism here, and in general, there's isomorphism here, and this is a Poisson chain complex. As I said, usually this is not commutative, but if I take just here, I change the Poisson module here, okay, where MT is M as R module. But with a new Poisson structure, say MA, the new structure is defined like this. This is the original Poisson structure over M, but I use the derivation, modular derivation. I think here this in R. We add a new term here. Because phi eta is a Poisson derivation, we always get a new Poisson modular structure. Then this is commutative. So we get the Poisson homology of R, the Poisson algebra with coefficients in a general Poisson module is isomorphic to the m minus p. N is a dimension R m t. It's like this. And if is the Poisson structure is unimodular, that means the modular derivation is log Hamiltonian. Then we get the usual dual Poincare duality. Okay, maybe I should stop here. But in polynomial case, as I said, log Hamiltonian may not be Hamiltonian. So in polynomial case, people call a Poisson structure is unimodular, means the Poisson derivation is zero. Is zero. But we have an example. There is a two-set duality, but no neutral duality, even for that kind of unimodular Poisson structure. Okay, thank you.